Does it work? Does this one work? Changes mine. Oh, do you have this one? Oh, she doesn't fit both. It's okay. I can use the keyboard.
Okay. Can you mute yourself on Zoom? We have the recording from the room.
Yeah, I think I'm muted already.
Okay. Sorry for a bit late because of the technical issue. Today we're very happy to have Yujin Kim. He's a postdoc from Caltech. He'll be talking about absolute continuity of non-Gaussian, Gaussian multiplicative chaos measures.
Great. Thank you, Yujin, for the invitation. It's really nice to be here. Okay, so everything I'll talk about today will be joined with Xavier Krischbaum, who's a postdoc at Toulouse. I'll have to keep going back and forth to my computer because there's no clicker. But so let's start with a one-slide overview just to get things started. Before we motivate anything, we'll just say what will be covered roughly. So we can consider a random Fourier series, also known as a random wave model, with i.i.d. Gaussian coefficients. Okay, and let's say we're on the space 0, 1 for simplicity. Okay, so the GKI will be i.i.d. standard Gaussians, and we'll have the cosines and sines as usual. Note this 1 over square root k normalization there. So that's exactly the normalization you need to see what is known as a variant of the Gaussian free field. Here we're on the unit circle. We can also consider not 0, 1, but more general bounded domains of Rd. And in particular, when dimension is 2, the model will exactly correspond to the Gaussian free field in the domain D. Okay, so I'll define all of the objects on this slide in due time, just to give an idea. Okay, so there's an associated measure with these log-correlated fields, or free fields if you want, called the Gaussian multiplicative chaos. So for the subcritical range of parameters, gamma between 0 and root 2, we formally define a measure by taking e to the gamma of this infinite series. Okay, so you define a measure by taking e to the gamma of the field with respect to the Lebesgue measure on whatever space you're looking at. This turns out to be this random multifractal measure. It's appearing as a universal object in modern probability theory. As I said, we'll go through all of this. Okay, so the question for this, at least for this one slide overview, is a very natural mathematical question. Everything here was Gaussian. Well, what happens when we replace the coefficients with general i.i.d. coefficients, non-Gaussian coefficients if you want? Okay, so in particular, one will show that we can still construct a chaos measure in this way by exponentiating the field. And the question is, what does the resulting measure look like? Does it look anything like a Gaussian multiplicative chaos measure? And we will answer this question through the lens of absolute continuity. So in particular, it will show that the objects are indistinguishable from each other almost surely. Okay, so that was a bit of a blitz. Here's the outline. So first, I will discuss log-correlated fields and GMC in a general sense and try to motivate everything with no assumed background. Then we'll discuss non-Gaussian variance and the status of the theory there. We'll give our main theorem. We'll talk about proof ideas. And time permitting, we'll discuss future applications of our methods that I think are rather exciting. Okay, so let's start. So very roughly speaking, a log-correlated field or random function with some size parameter n on a metric space indexed by n is a random function where the covariance blows up logarithmically with the distance between points. So as I'm getting closer and closer together, my covariance is exploding, but sort of like log. Okay, and n is some truncation parameter or modification parameter or whatever, some smoothing to smooth out this logarithmic singularity of the field. Okay, so it's a bit of an informal definition, but anyways, these things are a bit informally defined. So let's give some examples that might be of interest to folks here. So first example comes from random surfaces. So in 2 + 1 dimensions or 3 dimensions, you have these interface models like Ginzburg-Landau, various height functions of spin systems, Gaussian free field. These exhibit log correlations in this special 3D setting. If you're interested in random matrices, the logarithm of the characteristic polynomial of various mean field ensembles exhibit log correlations. Maybe you're interested in stochastic processes. well, branching Brownian motion, the local time field of a planar Brownian motion killed once it exits some large domain in 2D. Covered times of graphs by random walks. These also exhibit log correlations. And a particular cool example comes from number theory. So if you sample the zeta function on the critical line between like 0 and n, okay, so you're looking high on the critical line, and you look at the zeta logarithm of the zeta function on a unit interval around the sampled point, even this exhibits logarithmic correlations. Okay, so we'll actually revisit that a bit later, but yeah, it's a very, very fun example observed by, I guess, kind of starts with like Montgomery Sarnak and more recently Fyodorov, Harry Keating. Okay, so let's do two quick examples that I don't want to spend too much time on, but just to give some flavor, and then one example in more detail. Okay, so the two quick ones. First one comes from dimension 1. You can look at the circular unitary ensemble, which means you put the Haar measure on the set of n by n unitary matrices, and you sample according to that. So here I have the log of the characteristic polynomial. So when I take log of the product, I get a sum. And here, e to the 2 pi I lambda j are the eigenvalues. Okay, so the eigenvalues of un are lying on the circle, the unit circle. Okay, so this is a field on the circle. Theta is angled. And so using a result of Diaconos and Shashahani, it's a Taylor expansion. It's actually not hard to compute the covariance of this field, and one gets this logarithmic divergence. Okay, so I hid in this calculation because I said I want to be quick. Okay, so something more maybe lattice models flavor. You can look at the discretized Gaussian free field. So you can define this via this Gibbs measure on the screen. But notice this square potential. In fact, this turns out to be just a Gaussian vector of n squared entries, since I'm on the integer square side length n. And so if you just do a Gaussian computation, basically you just invert a matrix, you can compute the covariance, you can compute its asymptotics, it's related to Green's functions in this domain. And well, you see in this asymptotic expansion, you again have this logarithmic divergence as the points approach each other. Okay, so now for the example in a bit more detail, I want to talk about the binary branching random walk, which is a very simple model to define. Start with a single particle at the origin. Let's say we're on R now. Okay, so particles are walking around on the origin. The particle performs one step of a random walk. It splits into two, hence binary branching. And then each of these particles perform an independent branching random walk from this point forward. Okay, so these particles are walking and they're branching, and after some, I guess this is 6 time steps, you see particle trajectories that look like this. So you can see the system gets quite big, but you know, at 6 time steps, you can still see a binary tree. Okay, any questions so far? Okay, so in what sense is this a log correlated field, right? One needs to do a bit of gymnastics to see it. I should have used a different letter, but call capital N lowercase n the set of particles that are alive at time n. Okay, so this is your population. You have 2 to the n particles. So note that if I take the covariance of the random walks of 2 particles, what I get is just the time at which they branch. Why? Because let's say this is n, maybe they branch at some time s, okay, which means you will do some walk up to time s, and then they branch and do independent things. Okay, so this is Sn of a particle v, Sn, the random walk of another particle w. When I take the covariance, these are mean 0 independent increments, so of course they die in the computation. So I'm just left with the variance of the random walk at time s, which is just s. Okay, easy enough. Okay, now consider the covariance ball of particles. So if I fix some particle v, and I look at the particles that have covariance at least k with that particle, by what I just drew, that means that I have exactly the particles that branch from v after time k, right?
Excuse me, just for this notation. So in the end, is that the COV related to the covariance, or it's
COV is covariance.
it is covariance?
Yeah, it is the covariance of the random walks of v and w at time n. Yes, sorry. So v and w are 2 particles in my branching system. and then Sn is the random walk.
For the branching time, it's deterministic, yes?
In this branching process, it's deterministic.
It's random, yes? It's random.
Oh, no, it's deterministic here. Yeah.
Okay.
Yeah, so you can define it with random branching times too. Actually, it doesn't change so much morally speaking, but just for simplicity, it's deterministic. Okay. Given two particles. Okay. What time do we start, by the way?
5.
Yeah, 2:05. Okay. Right. So yes. So this ball, if you want, are the particles that branch from V after time k. Okay. So now to see the metric space, I'm going to embed the genealogical tree, which is just a binary tree, into 0, 1. And the way I'll do that is just let each subsequent generation occupy the next level of dyadics. Okay. So just take each generation and embed it dyadically. Okay. Well, then if this is my particle V, the BVK is exactly just the interval of size 2 to the minus k, which means if I want to increase the covariance linearly, my interval is shrinking exponentially. You just unwrap that is essentially saying that you have log correlations. Okay, so that might feel very unnatural, what we just did to see log correlations. But in fact, a big point I want to emphasize in this talk, and you'll see this in the proof ideas, is that log correlated fields are in strong analogy with branching random walks, in the sense that it's turned out to be extremely useful to find some kind of hidden branching structure in your log correlated field in order to analyze the log correlated field. Okay, so this is not the last time we'll see the branching random walk. Yeah, also known as the multiplicative cascade, kind of specifically in the setting of multiplicative chaos. Okay, so of course I'm giving all these examples because I'm building up to some universality for all of them. They should share some similar properties. And in particular, it's related to this thing I still haven't defined, which is called GMC. Okay, so many log correlated fields are known to become asymptotically Gaussian as n tends to infinity. This is true of the CUE, the discrete Gaussian free field is already Gaussian. Okay, so you can, for instance, think of your favorite object that converges to the Gaussian free field in the limit. So some examples, the CUE log characteristic polynomial, it was proved by Hughes, Keating, and O'Connell that you converge to the random Fourier series I had on the first slide. And dimension 2 example is Junnila. So if I take i.i.d. complex Gaussian entries from my random matrix, well, now your eigenvalues live in the unit disk, or unit, well, in the complex plane, but they concentrate in the unit disk. And in particular, you converge to a Gaussian free field in the disk. This is a famous result of Ryder and Virac. Okay, so that's the field. So asymptotically Gaussian log correlated fields are expected to exhibit universal behavior in their extreme values. And it's related to GMC. Okay, so here's one sense in which they are related. Oh, sorry, I thought there was a question. So if you look at the extreme level set of your field, okay, so here I have beta, some fraction between 0 and 1, and I'm looking at the values of my field that are larger than beta times the maximum. Okay, so if you want, I have my domain and I color in the points that are larger than beta times the maximum. So that's like extreme because you're on the scale of the maximum of your field. So of course, this is a very sparse set. This should converge to the GMC, this measure on the domain. A very related notion comes from exponentiating the field. Okay, so now I have this e to the gamma, where gamma is just, you can think of it as like a reparametrization of beta, or rescaling of beta. You can forget about this if you want. So I look at e to the gamma of my field. It's not so surprising that if I exponentiate my field, this measure is going to concentrate on the extreme values. And indeed, you should converge to this GMC with parameter gamma. Okay, any questions on this slide?
So GMC is a measure?
Yes, GMC is a random measure. So this dx is with respect to Lebesgue, but actually you can define it with a general class of reference measures. Great. Okay, so here's some pictures, simulations from Merrick Biscup's notes. So on both the top and the bottom, I have the discrete Gaussian free field. On the top, in color are the points around zero. So warm colors are the positive values, cold colors are the negative values. And this is a 300 by 300 square. And so you see these macroscopic contour lines between the warm and the cold, which basically means around zero. And it's a famous result that these contour lines scale to SLE4, okay? But we're not looking around zero. What we're looking at are the extreme values. Okay, so on the bottom, colored in are the values that are 0.5. You see this black thing, it's annoying. Okay, yeah, sorry about that. So, yeah, so you see it's getting sparser and sparser as I look at, as I increase the parameter of the GMC if you want. And it also has this kind of clustering fractal looking structure. Okay, so this is sort of what a GMC looks like if you want. On the other hand, I've plotted, or this is due to Michel Pin, e to the gamma of the field. So basically, these spiky things are supported on these sparse sets. Okay, great. So e to the gamma is the radon-Nikim derivative with Lebesgue. Okay, so what is GMC? So let's define things a bit more formally now. So in general, we start with a Gaussian log-correlated field on a domain, which is formally a generalized function satisfying mean zero and covariance that blows up with log, maybe plus a smooth perturbation, that's this F. Okay, so it's not a bona fide function because the covariance blows up, right? But you can realize it as a generalized function, as a distribution. In fact, it turns out to be an HS for any negative S, okay, in the solo space. This will not ever be referenced again, but just the point is it's rough, but not so rough. Okay. So the way we understand GMC is you start with some kind of smooth or continuous approximation. Let's call it H epsilon, the approximation to H. So something that's converging to H, right? And you define the GMC gamma associated to H to be the random measure that you get by taking the limit as epsilon goes to zero of exponentiating the field and normalizing by this expectation. Okay? So this is the GMC gamma associated to the log-correlated field H. So each Gaussian log-correlated field has an associated chaos measure. So oftentimes this approximating sequence is taken by mollifying or some martingale approximation. The limit is non-trivial in the so-called subcritical regime of gamma, so gamma less than root 2d. When gamma is equal to root 2d or greater, you just get zero in the end. Okay, so this is sort of the relevant range for this talk. And one thing I want to emphasize is I've defined GMC gamma associated to H, not H epsilon, right? Which is implying that whatever approximation I take of H shouldn't change the limiting measure. This is kind of a fundamental, this is, in a sense, this is like the starting point of the theory of GMC because, yeah, it's saying that the limiting measure is universal in the approximating sequence. Okay, so originally this was started by Kahan in '85. He was interested in turbulence, and he studied sums of independent Gaussian fields that converge to some log-correlated field. And later this was pushed by Robert Vargas, Shamab, and Nathaniel Beresticki. Okay. Great. So yeah, there's some original motivations and modern interest is coming from actually first finance and then connections with 2D Louisville quantum gravity. Okay, so as I mentioned, there's this universality conjecture. I want to just say that for the most part, the examples of universality that we've been able to prove are limited to Gaussian models, branching processes, and models with special integrability. So in particular, when you have a non-Gaussian log-correlated field that converges to a Gaussian free field, the theory still has a long way to go. And that's sort of a big motivation for our project, the project of this talk. So for instance, you have the C beta E where you have a lot of integrable formulas and you have nice representations. You have the classic GOE, GUE, GSE, and so forth. Beyond the results on the screen, there are actually not so many examples of convergence to GMC that we can prove. Okay, so let's continue the discussion of non-Gaussian log-correlated fields now. Aside from the fact that they are difficult to study even when they become Gaussian in the limit, some log-correlated fields are just not Gaussian in the limit. Okay? And for such fields, the corresponding chaos measure is then not expected to be a GMC. There's no reason to be a GMC. So the question is, what do we get then? Right? So let's give some examples, and I'll go through these a bit quickly because I just want to give an idea of the breadth of examples. But none of these will be the subject of today's talk. Okay, so first, this aforementioned Riemann zeta function. So if I take the log of zeta, I have a sum over primes of log of this thing. And it turns out that the non-Gaussianity is coming from the small primes. So somehow for large primes, they kind of block together and homogenize. There's this famous Selberg central limit theorem that says that if I sum primes between certain regions, they will converge to standard normal variables. But from the small primes, from p equals 2, 3, there's no such homogenization. They're just there, okay? Saxman and Webb in 2020 showed that for a random model of the zeta function, the corresponding chaos measure you get is absolutely continuous with respect to a coupled GMC. So in spirit, this is the closest result in the literature to what we prove. One thing I want to point out is this model turns out to be exponentially more Gaussian than the random Fourier series. Okay, so it'll be more clear what that means when I go into the proof a bit. But in particular, the random model of log zeta is actually exactly equal to a Gaussian field plus some smooth perturbation at all points. So yes, it ends up being very close to a Gaussian field. Okay, spectral measures of random unitary operators. It turns out that for a class of random unitary operators, the spectral measure you get from the spectral theorem, well, it's a random measure now. And for a general class, it's expected to get some kind of chaos. You're expected to see some kind of log correlation in chaos measure. There's kind of a miracle that happens for C beta E. Basically, again, these sort of integrable properties, properties related to sums of beta random variables, gives you a Gaussian thing at the end. But in general, you do not expect Gaussianity, and so in particular is posed by Gautier Lambert and Joseph Nazadel. If the question of whether or not these chaos measures you get from the random spectral measures are absolutely continuous with respect to some GMC. Critical stochastic heat flow. So this is a model I'm not so familiar with, but it is sort of very modern and a lot of active research going on here. So this is a log-correlated process of random measures on R2, constructed by Caravanas, San, and Zigoras. They have another paper that is literally titled "The One-Time Marginal of Critical 2D Stochastic Heat Flow is not a GMC." So the one-time marginal is a random measure, but they show that it's not a GMC by competing moments. And they also raise the question of what is the connection with GMC? In particular, can you find a GMC that is absolutely continuous with respect to the measure that they construct? And also mention that very recently, conditional GMC structure was found by Clark and Tsai. It's not something I know too much about, just for completeness, I'll mention it. Brownian multiplicative chaos. This is the chaos measure you get from exponentiating the local field time of planar Brownian motion. There, the story is rather complete. In particular, Antoine Jago has a number of nice works here. There, you benefit from the Ray-Knight theorem, which gives you an explicit relation with the Gaussian free field. And something that is kind of in very nascent stage is the log-characteristic polynomial of random permutation matrices. Actually, there hasn't been much progress on this story, and it's not clear what kind of object you should get from random permutation matrices. That's all I'll say about that. Okay, so this is sort of the state of the literature, or giving some motivation for studying these non-Gaussian fields. But the model for today is as follows. It's the same one from slide 1. So we're going to fix our domain to be 0, 1 in dimension 1 throughout the rest of this talk. We're going to take i.i.d. Fourier coefficients that have finite exponential moments and standard assumptions, and we consider this series. Okay, so I have S and A. N is the number of terms in the series. A is for these Fourier coefficients being labeled A. Okay, so it's some non-Gaussian distribution we take as the coefficient. In more general domains, we will ignore this on the next slide, but just to say, you can instead replace the cosine and sines by orthonormal basis of eigenfunctions of the negative Laplacian. And there, what you see is this object. So note that by the Weyl law, lambda k is k to the 2 over d. So then if I take lambda k to the minus d over 4, I get k to the minus 1/2, right? So I again see this root k normalization. So when I take the variance of S and A, I get a sum of 1 over k, which is log. So that's one way to kind of see a log appear. Okay. Yes, that's what I just said. And yeah, so these are exactly non-Gaussian analogs of the Gaussian free field. Okay, so here's some pictures in dimension 2 because it looks cooler than dimension 1. So here I have 20 waves, 50 waves, and 300 waves. So you see the negative regularity becoming more and more apparent as I add more waves. But we're going to focus on dimension 1 because actually all the main ideas are already present in dimension 1. There's the model again. The chaos measure, as before, is formed by exponentiating and taking that as the radon-Nikodym derivative with respect to Lebesgue. So note that S and A is a martingale because each of these terms are mean zero and independent of one another. And so when I exponentiate, I have a positive martingale structure. So when I condition on the first n minus 1 terms, well, the nth term pops out as mean 1, write exponential as a product. And so what I end up in the end is just the object at level n minus 1. I guess there's no way to get rid of this black box.
It's on your laptop.
Oh, I don't see it on. Oh, okay. It was on the dashboard. Okay, cool. Okay, so in particular, because we have a positive martingale structure for these measures, convergence is easy, right? That's just the martingale convergence theorem. But the question is, what do we get in the limit? In particular, nothing is guaranteeing that we converge to, that we don't converge to just 0, right? Okay, so there's the model again on the screen. So it was proven by Junnila that for the same range of parameters as a GMC, you get a non-degenerate measure. Okay, so that's nice. And again, for gamma outside of that regime, you get the 0 measure. He actually proves a bit more, but it's not relevant for this talk, so I won't mention it. And a big open question is this independence from the approximating sequence that I mentioned before. So this result of Kahan and others that actually, if you take a different approximation to the limiting field, S infinity A, you get the same measure. So actually, I put a star here because this is forthcoming work of myself and Xaver using ideas that I'll present in this talk. So in the end, we are able to prove universality of the limit under a, basically arbitrarily broad class of multipliers. Okay, and also one question that's left open by his result is, well, what does this measure really look like? What does it do? In particular, does it share properties with GMC gamma, which is kind of a classical object nowadays? Okay, so our result is as follows. For gamma in a slightly restricted regime, so the subcritical regime was between 0 and √2. Here we have gamma between 1 and √2, for reasons I'll explain soon. There exists a GMC of the same parameter coupled to the non-Gaussian chaos, mu gamma A, such that the two are mutually absolutely continuous almost surely. So if I take 2 samples of each, you cannot distinguish them with positive probability. Okay? We can be a little bit more constructive. We can actually construct a sequence of Gaussian Fourier coefficients coupled to the non-Gaussian coefficients such that the chaos you get from the Gaussian Fourier series is mutually absolutely continuous with the non-Gaussian Fourier series chaos. Okay. Yep, that's what I just said. In general bounded domains, we can prove the result for gamma between √d and √2d. And for people familiar with the field, you might note that the L2 regime is exactly in the complement of what we can prove. So the L2 regime is when the measure actually has finite second moments. So outside of this regime, you don't have second moments. You have like 1 plus epsilon moments. And in particular, the L2 regime is almost always much easier to study, in particular in light of this martingale structure, right? If you have L2 martingales, that's as good as it gets almost. So it's a bit funny that our result is the complement of this easier regime. And the reason will be made clear in the rest of the talk. But actually, our GMC strategy turns out to work for the full subcritical regime, given an additional input by a recent paper of Chowdhury and Ganguly. So we'll see that as a black box input, our proof to construct a coupling uses some high-dimensional CLT, okay, basically from another field of math. That's a very old general result due to Urinsky, dating back to the late 70s. So a recent preprint of Chowdhury Ganguly proves a new high-dimensional CLT that is a bit more tailored to, well, you just need more inputs, but we have them for the random Fourier series. And they show actually that replacing our use of Urinsky with their result and then following our proof strategy exactly yields the full subcritical regime, at least when the domain is a unit cube. So when the unit cube, when you have a unit cube, the eigen basis is expressible in terms of sines and cosines. You can make some explicit computations that their high-dimensional CLT needs, and yeah, things work. So we're very happy about this. And in particular, the result turns out to be true in the full subcritical regime. Okay. Okay, great. Are there any questions about the result?
What's the assumption on A? You have just mean zero variance and some moment bound on A?
Yeah, just finite exponential moments, basically. Yeah, zero mean, finite exponential moments. Yeah, so finite exponential moments is kind of necessary because we're exponentiating the field. Great. Oh, yeah.
So this high-dimensional CLT, is it?
So something like you sum a bunch of independent random vectors that can be arbitrarily long.
So is it an improvement over the, say, the classical?
So it's less general than Urinsky. But basically what you also need is some input on, for instance, the spectral norm of the sum of the random vectors you're adding together. And if you can estimate that, you get a bound in terms of that.
And which sets are you interested in? So high-dimensional CLT, you look at the difference between, say, the probabilities of certain sets.
Yeah, it's like total variation, for instance.
Total variation,
yeah.
so very, very strong.
Actually, even stronger, like L infinity norm between the two vectors. Yeah. Cool. Thanks for the question. So if everything's okay, then we'll start to discuss the overview of the proof. I'll try to keep things relatively simple, and in particular, I would like to demonstrate where we use this connection with branching processes. Okay, so first of all, you might be wondering where the Gaussianity comes from at all. This is actually not so hard to see. So if instead of the sum of the first n terms, I sum the first 2 to the n terms, okay, why not? Well, then I'm going to make these blocks of dyadically growing pieces. So, the mth block, if you want, which I'll call, not yet. The mth block has 2 to the n pieces. Okay, so now the orange numerator is i.i.d invariance 1 means 0. The denominator is root k, but root k in this range is more or less the same. It's square root of the number of terms. So just by the usual CLT, I should see a Gaussian as the block index is going up, right? As the size of these blocks is getting larger. So for a fixed x in my space, I'm becoming more and more Gaussian as m increases. Okay. So at the highest level, the Radon-Nikodym derivative is going to come from the low m's where we don't have this Gaussianity kicking in yet, and the Gaussian part is going to come from the high m's. Okay, of course, this is only for fixed points in my space. The space is uncountable. So we're going to need to discretize 0, 1 into a finite set. And once we do that, it will still not be enough. So we're going to use some ideas from GMC to pick a well-chosen subset of these bracketed terms here to couple with Gaussians. Okay, let's go into a bit more detail. So we're first going to replace 0, 1 with a discrete set. And the idea is going to come from the log correlations. So we're supposed to have high correlations when my points are closer than distance 2 to the minus n, right? Similar to this branching picture we saw earlier. Okay, so for 2 points that are closer than distance 2 to the minus n, my field should look relatively the same. And we can make this rigorous using a continuity and chaining argument. In particular, we'll be able to replace our field with something that is piecewise constant and just taking approximately 2 to the n unique values. Okay, so formally, this will be proved using the Lipschitz continuity of the cosine and sine. But morally, it comes from the log correlations. So here, replace means that if I look at the original field, or if I look at this piecewise constant guy, the corresponding chaos measures I get are absolutely continuous. Okay, so yeah, it's a reflexive property. Okay, so note that if at level n, so if the sum of the first 2 to the n terms, I replace my field with something that takes 2 to the n values, this is like replacing 0 and with a binary tree. As I increase n, the number of terms the number of values I need to consider increases dyadically. And given this sort of log correlation picture I tried to push earlier, it implies that my field should behave like a binary branching random walk as I increase n, basically as I send n to infinity. So a key caveat here is that in the branching random walk, you have independent increments. So the particles behave independently once they branch. This will, of course, not be the case because the field at 2 points are never independent, even if the x and x prime are very far apart. This poses quite a lot of difficulty. Okay, but the moral of this slide is just that my field is approximately determined by 2 to the n points. So successfully discretized 0, 1. Okay, so next, I want to couple with Gaussians using this idea from the very first, from a few slides ago with the colors and the brackets. 2 to the n is still going to be way too many for a high-dimensional CLT. And so the key idea to reduce 2 to the n to something smaller is that multiplicative chaos is supported on the set of so-called thick points. So this is related to the idea that chaos is coming from these extreme level sets. So the chaos measure is actually taking, in the limit, you can prove that it is fully supported on, in some sense, a limiting set of extreme points. And you can make some finite n version of this. Yeah, so of course, once you're restricting to only the points of the field that are very high, that reduces 2 to the n to something exponentially smaller. Because you're basically at the large deviation scale of your field now. So just to say it again, my field Sn is determined by approximately 2 to the n points, but from the perspective of the chaos measure, I only need to look at these thick points, which means I only need to look at points where my field did some large deviation in it. Okay. Right. So remember that increasing gamma corresponded to looking at more higher and higher level sets, extreme level sets. So in particular, the number of thick points grows exponentially as I decrease gamma, because I'm asking my field to do less and less extreme things. Okay, so this is essentially why we needed a lower bound on gamma, is because at some point you hit some regime where Urinsky is no longer strong enough to couple all the thick points. Okay, so yeah, this was really a black box input. So it turns out that the coupling tool that Chaudhary Ganguly developed is strong enough to couple all of the gamma thick points for any gamma between 0 and √2. Because it's a bit more complicated, in this talk, we're just going to use Urinsky, which might also be of independent interest. It's quite general. Okay, so after steps 1 and 2, we have discretized our field to something that looks like a binary branching random walk. And then we've coupled with a Gaussian model and a binary tree. But we've only coupled on the thick points. So away from thick points of the field, I have no control on the difference between these two fields. Okay, so so now, coupling on the thick points is only the right thing to do if you can actually show that the associated chaos measures with the coupled fields are mutually absolutely continuous, right? You can couple whatever points you want, but at the end, you need to prove the absolute continuity. So the obvious candidate for the Radon-Nikodym derivative is just to take the ratio of the Radon-Nikodym derivatives with Lebesgue, right? So e to the gamma of the difference of the fields. So the tilde just is how I denote the discretized field from the non-discretized field. Okay. So in order to show that the two measures corresponding to G tilde and A tilde, the Gaussian and non-Gaussian tree models, are actually absolutely continuous, I need to show various integrability properties of the R tilde that maybe you remember from standard measure theory class. So you need to show uniform integrability so that I can take the limit inside of the integral and replace Rn, this finite n radon-negative derivative, with some limiting measure. I need to show that the radon-negative derivative actually converges. In fact, it will not converge everywhere because our coupling doesn't exist everywhere. It only will converge on the thick points, but this turns out to be enough because the measures are supported on the thick points, and so forth. Okay, so this is actually where the bulk of the, so as an example, so we first need to prove this equality where the chaos measure of the non-Gaussian field satisfies this, and then you need to prove uniform integrability to push this limit inside and actually get a radon-negative derivative. Okay, so this is turns out to be the most technical step of the proof. It's where we really use the theory of multiplicative chaos to make explicit technical computations. And it's also the part we're going to emphasize the least in this talk. Basically not at all, because it is probably only of interest to people in the field. Okay, so let's talk about the discretization step now. Okay, so here's the diagram I had from before, where we have these blocks diagonally growing that are becoming more Gaussian. So I'm going to call this bracketed term here am tilde. Okay, so am tilde of x is a sum of 2 to the m i.i.d. things. So in the next slide, I'm just going to show by like a very easy computation that the covariance between 2 points should be approximately 1 whenever x and x prime are distanced 2 to the minus m apart. So m is the index of the block. Okay. So here's the definition of am tilde again. So I put the dot 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 sign because it just says ak2 cosine of 2 pi kx. So let's just focus on the cosine for now. Okay, so here's a quick heuristic. If I look at the difference between the am tilde at 2 points, well, okay, so I'm going to pull the summation outside. The ak1s and the square root k are all the same. It has nothing to do with x and x prime. And so what I just see is a difference of cosines and a difference of sines. Okay, so this root k is approximately the square root of the number of terms here, right? So without this difference of cosines, I have something that's just variance 1. This first part is just variance 1. So that's what I wrote here. But now I have Lipschitz continuity of my sine. And I know that the difference between cosine 2 pi kx and 2 pi kx prime is just k times the distance between the 2 points. So k is more or less 2 to the m. And so as soon as my x and x prime get closer than 2 to the m, I get something vanishing here. And this difference has vanishing variance. Okay, simple enough, but the point is we've realized what log correlations were telling us. Okay, so what it implies is that we can replace in our sum of n blocks, we can replace each of these blocks with 2 to the m values. Okay, so what does that mean pictorially? Well, okay, this is one of those things where to write out formally is maybe more confusing than just to like see a picture. So for the first increment, for the first block, I will identify it with just its value at the midpoint. And then all these other values are more or less the same as the value at the midpoint of the interval 0, 1. For the second block, I have 2 midpoints to consider. Okay, so everything in this interval is more or less the same as this point. Everything in this interval of size 1/2 is more or less the same as this point, and so forth, right? At each level m, I have 2 to the m unique values up to some vanishing error. So now if I want to compute my field at some point x, let's say x is here, and I'm looking at the sum of the first 3 increments, what I do is I just find the closest midpoint in level 3, I find the closest midpoint in level 2, I find the closest midpoint in level 1, and then I just sum up this tree. Okay. Yeah, so again, it's one of these things that maybe to write out formally is not so nice, but hopefully you can believe that there's some kind of scheme we can make that looks like a model on a binary tree. Okay. So yeah, I'll leave it at this level of detail for now. We can maybe revisit it later if we want. So I'm going to call S tilde this model that kind of looks like the binary tree model, the discretized version of S. Okay, so S n tilde in particular takes 2 to the n unique values. This is taking values on 0, 1. Okay, so because of this quick argument I showed earlier that the am tilde of x are piecewise constant on intervals of size 2 to the minus m, I can show that almost surely the supremum of the difference between the two fields is bounded. Okay, so this is kind of, well, yeah. And if the difference between the two fields is bounded for all n, well, it's not so hard to show that the chaos measures associated to each of them are going to have a bounded Radon-Nikodym derivative. It's basically just multiplying and dividing by 1. So this initial part is uniformly bounded, so I can just take it out, and then this second part is the thing that's converging to the chaos of the continuous field. Okay, this is just a way to make formal the statement that if the difference between my two fields is bounded in L infinity norm, then exponentiating them will also have a bounded result, bounded difference. Okay, so in total, we've showed that the continuous field and the discretized field have chaos measures that are mutually absolutely continuous, almost surely. Okay, so now we are only going to consider the model on the binary tree. So actually, you can even forget that it's a tree. Just know that S n tilde takes 2 to the n unique values. So n are the set of 2 to the n midpoints here, in analogy to the fact that at time n of a branching random walk, you have 2 to the n particles. So recall that S n tilde is a sum of these blocks. We wish to couple this with a Gaussian vector of the same covariance. The thing is, as I mentioned before, the crucial difference with the branching random walk is that the am tildes are not independent for different midpoints. Right? For different midpoints, they take values that are for instance, correlated through this cosine and sine. Okay. Also, there are 2 to the m of them, which is quite a lot. Okay. So what are we going to do? So first, note that I'm going to give up coupling all of the values of am tilde. So on all of the midpoints, I'm going to fix some subset that I'll call D. So D is just going to be the set that I have decided I'm going to couple on. Okay, so D is some subset of midpoints. And now I can write this as a sum of 2 to the m minus 1 independent vectors of length D. Okay, just like this. So each of these independent vectors is ak1 cosine plus ak2 sine, where the argument of the cosine and the sine are one of the midpoints in the set D. Okay, pretty simple vector. Here's the coupling result we use. So this is due to Urinsky in the L2 norm, so when P equals 2 in the late 70s, and actually was extended by some microeconomics folks in 2019 to any P between 1 and infinity. And so what it says is if you have the sum of a bunch of independent random vectors, then you can couple it with a Gaussian such that the LP norm of the same covariance of the sum, such that the LP norm can be bounded where the coupling error depends on the sums of the moments of the vectors you're summing. Okay, so it's, not so complicated of a right-hand side. The stuff is, it's stuff. It's some stuff that's going to be lower order, and I'm suppressing it here. So actually, we're going to take P equal infinity, as I mentioned earlier. This turns out to be the best thing to do, even in terms of minimizing this error. The CKs are these, AK1 cosine plus AK2 sine. And I'm sure you can believe that computing these moments is not so hard, because in particular for fixed K, there's only 2 sources of randomness. Everything else is cosine and sine, which are bounded by 1. Okay, so making, doing the most straightforward computations gives you the following coupling error. If I want the L infinity norm between my coupled Gaussian to be less than m to the minus 2, I have to pay this bound here. So I have exponential 2 to the minus m over 2, where m is the number. So this is related to the number of vectors I'm adding together. and d is the number of points I'm coupling at. So you see a competition between the number of points I want to couple at, that's the length of these CKs, and the number of vectors I'm adding together. Okay, so by the way, for the zeta function, it turns out that this 2 to the minus m over 2 becomes 2 to the 2, 2 to the minus 2 to the m over 2. So it's doubly exponential. So that hopefully clarifies why I said you're exponentially more Gaussian in the zeta case. Okay, so first of all, note that clearly you cannot take d to be 2 to the n, or to be the full set of midpoints, just size 2 to the n. Okay, in fact, you can only take it to be at most 2 to the m over 2 points if you want to use Borel-Cantelli and say that eventually, almost surely, the all-infinity norm between your Gaussians and non-Gaussians is summable. Okay, so what set are we going to take? Well, we're going to take these thick points. Okay, so a key fact of Gaussian multiplicative chaos, actually Gaussian is not so important. We showed in our paper it's easy to reproduce the proof in non-Gaussian setting. It's supported on the set of gamma thick points of my field. So these are the points of my field that kind of have drift gamma times log 2. Okay, so if I fix an x and I just increase n, this is a bona fide random walk because I'm adding independent increments. Okay, so it's basically saying my random walk, which typically has scale root n, is actually linear in n. And the measure of the chaos, the complement of thick points is 0. Why is this true? Why should we be supported on gamma thick points? Well, here's a Gaussian heuristic. So if I have a Gaussian with variance log 2n, like this s tilde n does, this s tilde n has variance log 2n, that's a computation. Of course, typically I'm going to have size root n, not n. But under this Gersonov transform, it is a theorem that the mean becomes shifted to gamma times log 2n with variance, with the same variance as before, so with standard deviation root n. So this is an elementary fact about Gaussians. And so this GMC looking tilt is basically tilting my field to want to take values order n, or order gamma log 2n on average. And in fact, you can prove that if you sample a point from GMC, almost surely you're going to get a thick point. Okay, so in particular, it should be sufficient to couple along level n thick points. So there's a limit here. We don't want that. We want something for finite n. So what we do is we just reduce gamma by a little bit. Delta is just any positive number. Okay, so this is our idea, and this is validated in step 3. But at least for step 2, let's see what kind of coupling we get from Urinsky. If we take D to be the set of gamma thick points, so this is the bound we had earlier. How many thick points are there? Let's approximate the thick points by the first moment of the number of thick points. So there are 2 to the n points I need to consider, 2 to the n midpoints. And then for each I multiply by the probability that you're larger, the random walk at time n is larger than gamma minus delta log 2 n. Okay, so just using a Gaussian tail bound, I have this square decay. And plugging it back into Urinsky, I factor out the n over 2, and I have this orange part as my decay. So you can see as soon as gamma becomes larger, smaller than 1, I'm actually not decaying anymore. So this is why we have this limiting threshold of 1. And yeah, as I mentioned before, the same steps, but instead of using this coupling bound, we use the one of Chaudhary and Ganguly. You can actually recover all gamma. All right. Yes, and then you can use Borel-Cantelli. So this last step, as I mentioned before, is just going to, at the level of this talk, will just be summary. So we've constructed this discrete tree model from the continuous Fourier series in step 1. In step 2, we did a coupling between a Gaussian field and a non-Gaussian field on the tree, such that the difference is small only at the thick points. Okay, so away from this sparse set of thick points, I have no control. In fact, step 1 is invertible in the sense that I have this Gaussian tree model, but I can actually invert it to construct a Gaussian Fourier series such that the Gaussian tree model and the Gaussian Fourier series are close in the same way that the non-Gaussian tree model and the non-Gaussian Fourier series were close. So I sort of have this diagram, right, where the arrows represent mutual absolute continuity. And it remains to prove that the tree model chaoses are mutually absolutely continuous. In particular, coupling at the thick points was only the right thing to do if we can actually validate this third step. And as I said about 10, 15 minutes ago, this is sort of where the heart of the chaos computations lie. Okay, so maybe in my last couple of minutes, I'll just quickly discuss some future applications of our methods. How much time do I have in total? An hour or?
Yeah, it's almost the end.
Okay. Let's see. I can go. I can just make this like 2 minutes or something.
Yeah,
so
2 minutes.
I'll go fast and you
Yeah.
can ask questions. Okay. So as I mentioned before, universality in approximating sequence is kind of the foundational first step in GMC theory. For non-Gaussian theory, the theory is very much in its nascent phases. In Kahan's original work, we can look for some inspiration. So we take the log-correlated field to be a sum of independent Gaussian fields with some regularity conditions. And so we can just start by trying to prove universality for these kinds of non-Gaussian log-correlated fields, ones that admit a decomposition into independent non-Gaussian fields with some regularity. Okay, so this is work in progress with Xaver. We're able to show some partial universality for these kinds of log-correlated fields and complete universality for the random Fourier series. Okay, moving quickly. The critical chaos corresponds to this parameter gamma equals root 2d, the boundary between when you see a zero measure and something non-trivial. In fact, you can renormalize the measure to get something non-trivial known as critical GMC. It turns out to be very important in its own right. But there are many complications that arise from this renormalization. In particular, the critical GMC for the most part has only been constructed for Gaussian log-correlated fields or log-correlated fields that have some rather explicit branching structure and integrability structure. In particular, it hasn't been constructed for the model that we discussed today. So in forthcoming work with Xaver, we're going to show that our thick point coupling method with the GMC can actually be used to construct critical chaos for non-Gaussian log-correlated fields. Basically, by doing this coupling, we show that we can circumvent a lot of the issues we have by not having a Gaussian field.